so yeah, I think I'll first try to sketch the proof, or maybe at least main steps in the proof of the remaining implication, and then return to some of the questions which we briefly discussed before, but maybe given more details. So that we want to show that Holt's embedding conjecture implies Kirchberg. Right. And yeah, this is will be kind of even more hairy than before. So the goal is to give just some details, and so originally this was proved by Kirchberg, but the proof for our sketch is due to Ozawa. And it goes as follows. So let us start with the following construction. So suppose we have a sister algebra A, and O is a tracial state. So as we know, then we have a GNS representation with state given by then some vector psi tau. And as we discussed yesterday, then we also have the Woodrow conjugation operator, which defined by like this, and the role of this operator is that if we take the von Neumann algebra generated by this A, then we get exactly the commutant of this von Neumann algebra. So out of this, we can construct then a representation of the. So we get a representation. In addition to the representation pi top of A, we also get the second representation of the opposite algebra, which I will denote phi prime of 2 of the opposite algebra on the same Hilbert space. And by opposite algebra, I just mean exactly the same vector space. Everything is the same, star structure, norm, everything this is the same, but the product is the opposite. So what we had before, one can check that this is still a sister algebra. Namely, so we use this identity motivators. So we take a representation of A star and then conjugate by J2. So you do need the star to get linearity, because remember that J2 is an anti-linear operator. So to get really a linear linearity in A, you need to put the star, and as a result, you're not going to get a representation, but only anti-representation. That's why we're changing the order of multiplication. Now, because of this identity, these two representations commute. So as a result, we get also a representation denoted by times pi prime of the maximum and the product of A with A op on the same Hilbert space. And using this representation, we get out of our tracial state now a state on this tensor product. We simply define, let me call it for tilde. So this is a state on this sister algebra, and so we just defined it using this representation, right? And the same vector which we used to define tau. Yeah. Or more concretely, if you look at the definition, then this just means that tau tilde of A times B is simply tau of AB. That's a linear function we get, and according to this construction, this is actually a state of the maximal tensor product. And moreover, if you start with this state, then this representation is simply the GNS representation corresponding to this state, because we already have a cyclic vector and a representation. So in other words, you can simply say that the GNS representation corresponding to this new state is this product representation of the maximal tensor product. Okay. Okay, so that was the preparation. Now we assume that Kohn embedding conjecture is true. So what does it give us? We'll now take any ratio state, state 2 on the group system algebra of the free group with infinitely many generators. So according to one of the reformulations of a Kohn embedding problem, this then means Kohn embedding problem of conjecture implies that we have there exist representations phi m of the system algebra on some finite dimensional Hilbert spaces such that our trace is given by simply the matricial traces in the limit. So in other words, that store of x is the limit when n goes to infinity of matricial trace applied to pi of x for every x in the system. Right? Okay, so what does it give for us? So let us call this trace 2m of x. So we get certain traces on this system algebra, which actually factor from matrix algebra, and which approximate our given trace in the weak star topology. So if we look at these traces, yeah, then the corresponding trace, so the corresponding trace T and tilde, yeah, this certainly factors through the this system algebra, minimal tensor product of C star and F infinity of, right? Simply because we're dealing with finite dimensional system algebras here, and the tensor product, maximal tensor product of this with itself is the same as the minimal tensor product, right? So we go. As a result, but since Tor is approximated by these traces, we can conclude that the same is true actually of the limit state trace Tor. So hence, the same is true. For Tor. Right. And what this implies that, okay, so these states factors through the minimal tensor product, and this means that the GNS representation of this state factors through this tensor product. Okay. Therefore, the GNS representation of this state, which is C star algebra, so the representation of the maximal tensor product of the group algebra of F infinity with the opposite one. So this implies that this one must factor for the minimal tensor product. Okay. So So this is something, but this is not exactly what we need. So what is left to show? So in the end, we want to show that these two tensor products are the same. The fact that we are using the opposite now in one of the factors does not matter, because for any group algebra, the opposite sister algebra of the group algebra is isomorphic to the group algebra itself. So note that, that for any group gamma, we have an isomorphism, of course, of the algebra opposite to the group algebra with the group algebra itself, which simply maps G to G inverse, right, and extended by linearity. So therefore, these opposites do not matter. I want to show that these two, therefore, I want to show that these two tensor products are the same, so the norms are exactly the same. But what we conclude from Kohn-embedding problem is that actually for any threshold state, tau, at least this representation factors from this one. So therefore, to finish the proof, it would be enough. So, to finish the proof that the maximal and minimal tensor products are the same. It suffices to find one threshold state, to prove the existence of such a threshold state or such that the corresponding representation is pi to tilde, so the GNS representation corresponding to this state is faithful. Right. So up to this point, everything was sort of rigorous, legitimate, but from this point, more hand-waving. So the claim now, and this is the main part of the argument, that such a state exists indeed. And here, the claim is that such a coexists. And the question of why. So let me give some indication why this is true. So how do we construct norm on the maximal tensor product? So in the end, we can find, by definition, we can find a representation. Find a representation pi, say pi1, of infinity on V of H, and some representation pi2 of CS star F infinity of, well, more precise, op on V of H, such that these two representations commute and define as a faithful representation of the maximal tensor product. This is how it is defined. So such that pi1 A commutes with pi2 of B always. And the corresponding representation pi1, pi2 is actually faithful. Right? So therefore, the claim is, if we compare these two statements, that what we need to show that somehow starting from one such representation, I should be able to construct a representation of this type, which is still faithful, or maybe at least a family of those. I would be fine with that. Okay. And so here are the indications why this can be done, but again, to do it rigorously, one really needs more tools. So this will be really just a sketch of an argument. So we will do a number of reductions to kind of get better and better representations. So the first thing we can do is that we can actually assume that if we start with a von Neumann algebra, so let me write this von Neumann algebra to be a von Neumann algebra generated by the first factor inside B of H. And then the second representation represents an algebra in the commutant of M. And generally, we have no kind of easy relation between M itself and the commutant. But the first deduction claim is that we can actually replace, we can assume that we're in a standard form, meaning that M prime is JMJ for suitable J. Why is that? Well, basically because the von Neumann algebra always have some representations with this property, and general representation theory of von Neumann algebras was mentioned. This is quite easy, so you can always construct any other representation from another faithful representation. So basically by doing some multiplicity, or maybe stabilizing by B of H, you can achieve these kind of properties. Okay. So this is a if one accepts that one such representation exists, this step is not difficult to realize. Okay. The second, but this is still not about not in terms of some trace, so it is just for some J. Look at this. Okay, next thing you can assume, we can sort of double the size of our representation. So we can consider a representation y to be y1 plus, let me call it y3, where so I can assume then that the representation phi2 is of the same type I defined before, but some other representation. Or in other words, phi3 now of A is J phi2 of AJ. So in other words, I have a copy 2 of representations, and then if we take a direct sum of them, so we can actually assume that this phi2 is equal to phi1 prime. So in other words, meaning that phi2 of A is J phi1 of A star J, right? So I just double the size of the of our Hilbert space, and I will still get, at least in some off-diagonal terms, the required products. Okay. Right. So okay, so we're in the situation where these two representations, so we have just pair of representation, but they are related by these formulas. So the next step is that, again, this is something that one has to use from modular theory. So there is always a possibility to pass from type 3 or general von Neumann algebras to type 2 infinity algebras. So the modular theory provides us with the possibility of going through term 3 to type, well, at least 2. Yeah. So there are kind of two steps here which haven't been explained in any way, and for this you really need a modular theory to explain it rigorously. One is that you can actually do this type of representation, and the second that you can go from any representation of von Neumann algebra or from any von Neumann algebra in some way to a type 2 von Neumann algebra. Okay, but once you get this, you are not very far from what we need, because as was I think mentioned by Robin, so what is a type 2 situation? This means that the unit can still be infinite, but you have some trace which might be infinite, but you must have also many finite traces. So we can find finite projections. Finite projections in M such that Pn would converge to 1 in the strong operator topology. And then what we do, we reduce our representations by these projections. But you still have to do something. So basically, we want to replace pi by maybe pi n, which is kind of reduction of pi by p, right? So to get inside the finite von Neumann algebra. But this cannot really work because this is just a completely positive map, not a homomorphism. But it's not difficult to modify because we're dealing with a free group. So out of generators of the free group, you get certain contractions, but then you can use the standard derivation technique to extend contractions to unitaries. So this is not quite a representation, but from this you can get true representations of f infinity infinite von Neumann algebra. So in other words, algebras equipped with a trace. Okay. So if you perform all the steps, so you end up with a faithful family of representations of this type, and then finally you can just take a combination of these traces, or you can consider the fact of the entire family. It doesn't really matter.
Is it correct to say, because you described effectively you are just working with this first representation, pi1, right? But you take pi2 with you, so to speak, right?
Yeah, so at this step I'm taking pi2 with me, so I have sort of double representation. As a result, I consider not two different ones, but really just one, and then the second one obtained by this kind of operation. So this is kind of easy step. Even without modular theory, I think it's difficult to make sense of this. But if one accepts modular theory, one really has to check something. I would say there are kind of two steps here. It is this one. First, you embed your general von Neumann algebra in type 2 infinity, and you still have to see what happens exactly under these representations. And you have to convince yourself that everything is going to be fine there. This is one computation one has to do. And the second part is basically there, because what could possibly go wrong is that if you're not very careful in how you kind of modify completely positive map into representations, you could lose your faithfulness. Right? So somehow you have to be careful enough so that you're not going to add some sort of additional elements to the kernels of this representation. Both things are not too difficult to check, but this certainly goes beyond what I can and want to cover. So that's more or less a sketch of the Prof.
Just to understand, so this claim is independent of the common embedding.
Yeah, this is independent. This is a rigorous claim which is proved. But it's somewhat kind of maybe one thing to mention. It's a kind of a rather delicate claim because, for example, it's not claimed, right, that these traces to n come from just some finite dimensional representations. So they just come from some finite von Neumann algebras. And so to kind of illustrate the subtleness of this, so in addition to residual finiteness of groups, one can talk about residual finite dimensionality of sister algebras. In other words, it has a faithful family of finite dimensional representations. And here it's known basically by this type of technique, by result of Choi, that this sister algebra is residually finite dimensional. So you can have a faithful family of finite dimensional representation of this is the algebra. But it is not known whether it's true for the product of this. So at least that's why I understand.
Well, it depends on whether you believe in that, because this is actually equivalent to common heading.
Is it?
Yes, yes.
Okay.
It's not obvious, but it is.
Okay, then it means that it's actually wrong. Right? But then this shows kind of the delicateness of these things. That you manage to construct these states, but they're not really coming from something finite dimensional. You're really getting somewhere inside some strange like the one factors, yeah. Okay, yeah, that was what I wanted to finish with as a lecture, but as a tutorial, I can discuss one of the questions which were swept under the rug. I don't know. Are there any particular requests? I have to choose. Okay. That's something. Yeah. Let me do the following question. So, maybe to just illustrate a couple of subtle points in some of the arguments, and both of them were asked during the lectures. So one was, like, if you want, relatively one. So suppose you have an increasing family of injective algebras. And I want to show directly, without passing to commutants, that the limit is also injective. So we take the union and take the closure in the root operator topology. So an attempt to show this is that you take En of x, so En is a conditional expectation from B of h in M of n. And you want to construct out of this somehow the conditional expectation. The suggestion was to try something of this sort. When n goes to some free outer filter omega of En of x in the, say, strong operator topology. Why this is not going to, or at least it's not obvious why this should work at all. And the issue is the following. So how do you check that Ex is equal to x for x in for all x in M, right? Of course, you can, if you approximate, so you take any element. So this is certainly true for all x in the union of all these M_Ns. But the map you get is usually discontinuous. So there is kind of no way of checking this for arbitrary x. So if E of course is a normal map, then everything is fine. But otherwise, it's problematic.
When you say discontinuous, is it only in the weak or strong operator topology discontinuous, or
I mean, in the non-topology, it's fine. It's a unit or completely positive map. Everything is fine. But in any other operator topology, it's bad. Okay, and another point was it's a question Jacek asked. I didn't quite answer that. So we proved that if we have this situation when we have a sister algebra inside B of H, right, and we have a ratio state which is cyclic. And so for this ratio, this already implies that Tho defines you a faithful state on the entire von Neumann algebra. This implies that this Tho is faithful on the entire von Neumann algebra generated by M. And then the question is, well, do we really need ratio property? Can it be that this is true actually without this assumption? It is not, so a similar result for a similar property is not true. Even if you assume that's the important thing, that even if you assume that this state is faithful on the entire sister algebra, it can still be non-faithful on the von Neumann algebra. It's true for faithful general states. So in other words, do this formula. So let's assume that we have so we assume that A again inside B of H. We have a unit vector which is cyclic, and we can see that the state faithful on A. So we want to show this that this does not imply that phi is faithful on the von Neumann algebra generated by A. So you really need a bit more than just faithfulness. So I will give a counterexample, or example where but if someone knows a better example, just let me know. How to construct such an example. So let's start with any, so we take any unito simple infinite dimensional sister algebra. Anything you want. For example, the reduced sister algebra of the free group. In this case, it has tons of inequivalent irreducible representations. So we take any two of them. So take two inequivalent irreducible representations. Phi 1, phi 2. So let's say phi y from A to B of HR. I want a separable one. So that this Hilbert space is half-finite dimensional. And then in one representation, I will take a faithful normal state, and in the other representation, I take non-faithful state. So let's say phi 1 is phi 1 raised by 1 rho, where rho is with 0 kernel. So some faithful state of this form. Okay? And as a second state, I take any pure state. dividing H2 is 1. So the point of, since we have two inequivalent representations, if you take direct sum of these representations and take the von Neumann algebra generated by these things, you get that this is B of H1 plus B of H2, basically by Schur's step and irreducibility. And now you can do the following. Now as my state phi, I take converse combination of these two states. And then GNS representations are easy to describe for each of them. So for the first state, the GNS representation is simply a representation of is just pi 1 and the 1 on H1 bar, which is thought of the Hilbert-Schmidt operators over H1, and the corresponding vector. This is how it's explained in Robin's notes, rho 1/2. And the second GNS representation is just representation pi 2, of course, with vector given by this choosing vector psi. So out of all of this, you can compute, if you sort of stare at this, that representation, GNS representation corresponding to these things, is still just a direct sum of these two representations. So, and this is really a representation in Hilbert-Schmidt operators on H1 plus H2. And the von Neumann algebra generated by this thing will still be the von Neumann algebra H1. So acting on this space of Hilbert-Schmidt operated multiplication on the left plus pi 2. Well, so von Neumann algebra, so B of H2. And corresponding vector will be the vector given by this. And out of this, you see that this is not going to give you a faithful state on the von Neumann algebra. It's has a huge kernel on the second vector. Okay. So, I mean, anyway, punchline of the moral of the story, yeah, one has to be careful with faithfulness of states on.
Why is this state faithful on A?
Oh, it's already the first one is faithful, right? So I assume that the kernel of R is 0. So already the first state phi 1 is faithful. So there comes this combination of faithful.
Phi 1 to be faithful?
Hmm?
You want phi 1 to be faithful?
I mean, I said it's a simple sister algebra, so
okay.
it's so whatever, we don't have to think. So already phi 1 is faithful, so this is a faithful state. It's not going to be faithful for nothing else. Okay. I don't know. I think I'll stop here.
Any questions or comments? Finished today's session. In that case, let's thank.
Oh, yes. Go ahead. Yes.
tried using Hamana's
Sorry?
instructions on question 1?
Yeah.
Yeah, you have.
Sorry? So what's
So the question is, Hamana has this way of getting the injective envelope as via minimal semi-norms.
Mhm.
And if you look at En of x norm, then that's increasing, and so that converges to a semi-norm. So I wonder if there's a way to use Hamana's minimal semi-norm business get that result without the
Yeah.
commutans.
I don't know, maybe, but it can be that we still get something with injective envelope rather than the entire phenomenon algebra. So I'm not sure we will really get all the way to the union, to the entire phenomenon algebra. But I don't know. Yes, so the main point was that read is pass to commutants, and at the level of commutants it works perfectly fine. Then one doesn't have to struggle.
Any other questions or contributions? Well, I think we can thank the operator over those crowds because they've done their bit now.